have you ever just stopped and wondered, what's really going on inside an AI's brain when you ask it a question? Well, today we're going to pull back the curtain. We're going to follow one single sentence on its secret journey through a large language model, and we're going to see exactly how these things learn to understand us. You ready? Let's get into it.
So it really all boils down to this one huge question. Can a computer actually talk like a human? I mean, for years, this was just stuff you'd see in the movies, right? Science fiction. But now, it feels like we're right on the edge of making it a reality. So the real puzzle is, how do you teach a machine, a box of silicon and wires, to get the subtlety, the humor, the meaning behind our words?
And look, this isn't just some abstract, techie thought experiment. This technology is already all around us. It's the chatbot you argue with about your phone bill. It's the magic behind a smart factory running perfectly. It's even the voice assistant in your car that, mostly understands what you're saying. If we want to get a handle on the world we're building, we've got to understand how this stuff works under the hood.
Okay, so let's do it. Let's follow that sentence. Picture it. The second you hit enter, our sentence starts its journey. And its very first hurdle is a big one: translation. But we're not talking about translating from English to Spanish. No, this is much more fundamental. It's about translating our messy, beautiful human words into the only language a computer speaks: plain old numbers.
And that first critical step has a name: tokenization. You got to remember, a model has no idea what cat or happy means. It can't read. All it sees are numbers. So job number one is to take our language and chop it up, then swap every piece for a number, like a secret code.
So yeah, tokenization is basically the bridge from our world to the machine's world. It's like building a massive dictionary where every single word, or even a piece of a word, gets its own unique ID number. Simple enough, right? Well, as it turns out, how you build that dictionary is kind of a huge deal.
You could try a couple of obvious things, like why not just give every single word in the English language its own number? The problem is your dictionary would be gigantic. And what happens when someone makes a typo or invents a new slang word? It breaks. Okay, so what about the other extreme? Let's just use individual letters. The dictionary would be super small, right? Just A, B, C. But then the poor model has to waste a ton of its power just learning how to spell the. Yeah, neither of these is a great solution.
And this is where modern LLMs get really clever. They use a kind of hybrid approach called sub-word tokenization. And honestly, it's the perfect middle ground. It's the best of both worlds. It can handle common words in one go, but if it sees a weird or super long word, it can just break it down into smaller, recognizable chunks.
The go-to method for this is something called byte pair encoding, or BPE for short. And the really cool part about BPE is that it doesn't come with a dictionary someone made for it. Nope, it builds its own dictionary completely from scratch, just by reading a ton of text and figuring out which letter combinations show up most often.
So here's the play-by-play. Imagine you just have a massive soup of individual letters. BPE scans through and says, the letters E and S appear next to each other all the time. So bam, it merges them into one new token, E's. Then it does it again. You know what? E's and T are a super common trio. Bam! Now est is a token. It just keeps doing this over and over, merging the most frequent pairs, building bigger chunks like ing or tation until it has this super efficient custom-built vocabulary.
All right, so step one is done. Our sentence isn't words anymore, it's a list of numbers, these tokens. But right now they're just labels. They're meaningless. Number 5257 doesn't mean anything. So the next big step is to actually inject some meaning into these numbers. And we do that with two key tricks: embedding and positional encoding.
So in embedding, what it does is it takes each of those simple token IDs and blows it up into a long list of numbers. We call this a vector. Now, the best way to think about this vector is like a coordinate. It's a precise location in this giant, invisible map of meaning. And on this map, words that are similar in meaning, like king and queen or running and jogging, end up being neighbors.
And the scale of this meaning map is just mind-blowing. I mean, check this out. A relatively small model like GPT-2 gives every word a coordinate with 768 numbers. But then you get to something like GPT-3, and that coordinate has over 12,000 numbers in it. That's how it's able to capture all the tiny, subtle differences in meaning between words.
Okay, but hang on. This brings up a big problem. If every word is just a point on this map, how on earth does the model know the difference between the dog chased the cat and the cat chased the dog? The words are the same, the meanings are there, but the order changes everything.
The fix is actually pretty genius. It's called positional encoding. Basically, on top of the meaning vector, the model adds a second vector that just contains information about the word's position. It's literally like giving each word its own little GPS coordinate in the sentence. You are word number 1, you are word number 2, and so on. This gives the model that crucial sense of order and grammar.
Okay, so now we've got our tokens. They have meaning, and they know their position in the sentence. Now we get to the real magic, the absolute core of what makes a modern LLM tick. This is the part that lets it understand context like never before. It's called attention.
Self-attention is all about letting each token in the sentence ask itself a very simple question. To understand what I mean right here, right now, which other words in this sentence are the most important? It's a way for the model to draw lines, to create connections between words, even if they're on opposite ends of a long paragraph.
And it does this with a really neat little system using 3 special vectors. The easiest way to think about it is like a little conversation. The token we're looking at sends out a query, which is like it's shouting, "Hey, I need info about places." Every other token holds up its key, which is like a little sign that says, "I'm a location" or "I'm an action." If the query matches a key, then the first token says, "Great, give me your value," which is the actual information that token holds. It's a little marketplace of information.
And by doing this for every single word, the model builds this incredible web of connections across the whole sentence. It calculates these attention scores that map out all the relationships. So in a sentence like, "The robot picked up the ball because it was heavy," the attention scores for the word "it" would point straight back to ball, not robot. And right there, that's how true context is created.
So we have all these cool pieces, attention, neural networks, but they don't just float around randomly. They're neatly packaged together into a single repeatable building block. Think of it like a Lego brick. And this brick is the absolute backbone of the whole model. It's called the transformer block.
And this block follows a very specific recipe every single time. First, the sentence goes through that fancy attention layer we just talked about to figure out who's talking to whom. Then, that output gets passed to a simple neural network. You can kind of think of this as the thinking part. And these other add and norm steps are just there to keep everything stable and running smoothly. The real power comes from stacking these blocks, one on top of the other, sometimes 90, 100 times or more. Each layer gets a slightly deeper, more abstract understanding of the sentence.
So let's recap. Our sentence has been chopped up, turned into numbers, given meaning and position, and then processed through this huge stack of transformer blocks. The model now has a really rich understanding of it. But how good is that understanding? How can we actually put a number on how smart one of these models is?
Well, one of the main ways we measure this is with a metric called perplexity. And it's actually a pretty simple idea. Perplexity is basically a measure of how surprised the model is by a piece of text. See, a really good model should be able to predict the next word in a sentence pretty accurately. If it's constantly getting it right, it's not very surprised, and its perplexity score is low. That's good. But if it's always confused and making bad guesses, it's highly surprised, and its score is high. That's bad.
Here's a great way to think about it. If a model has a perplexity score of, say, 10, it means that on average, it's as uncertain about the next word as if it were choosing between 10 different equally likely words. A score of 3 means it's narrowed down the possibilities and is way more confident. So the entire game, the whole reason for training these huge models, is to get that perplexity number as close to 0 as humanly possible.
And that's it. That's the end of our sentence's incredible journey, which leaves us with one last, pretty mind-bending question to chew on. Think about it. All of this insane complexity, the tokenizing, the embeddings, the attention mechanism, it's all designed to do one thing: reduce a machine's surprise at our language. So what happens? What does our future look like when a machine is no longer surprised by anything we say? Something to think about, isn't it? Thanks for coming along on this little trip.